Greetings! Welcome to our 7th installment of Vertex Operator Algebras. Today we will be discussing some additional structure on modules that might be familiar from our discussions of algebra. Namely, we'll discuss graded and product modules. So let's start with the graded ones. Consider three characters in this play: U, G, and V. U is an abelian group. Remember, that's supposed to be a fraktur A. G is a Lie algebra that is U-graded, and V is a G module. V is said to be a U-graded G module if two conditions are met. First, as always, V must be a U-graded vector space. Second, the action of any element of G with degree alpha on the subspace of V that is homogeneous of degree beta must belong to the subspace of V that is homogeneous of degree alpha plus beta. If we further restrict U to be a subgroup of field addition, then we learned in section 5 that G has a degree derivation, D. Because of this, V is also a module for the algebra of G with D adjoined to it. And in this particular case, D is an operator that plays double duty as the degree operator on V. Did you get all of that? I'll repeat it. D is a degree operator on G, but it is also a derivation because of U. So it's also the degree operator on V. Let's see how this works in practice. For A and G and V, D acting on A acting on V yields the eigenvalue alpha plus beta because it acts on both objects. See? Confusing. Let U be an abelian group that is a subgroup of some larger abelian group, say B. You see, U really should have been fraktur A, because that's fraktur B. Given some U-graded G module V and some beta in B, we can shift all of the degrees of the homogeneous subspaces of V by an amount, beta. Now, this discussion can get confusing, particularly in FLM because we're going to chase around all these abstract indices. Suffice it to say that any missing homogeneous subspace of V not present in the original U grading is fixed to be the trivial zero-dimensional vector space. More precisely, they are the subspaces V sub gamma, where gamma is in B but is not related to any element of U by the addition of beta. Whew, okay, enough of that. Let's talk about product modules. As a warm-up, let's consider two distinct representations of a Lie algebra G on a vector space V. Let's call them pi left and pi right. Evidently, the map pi left plus pi right is also a representation of G on V, and note that the representations commute. Armed with this fact, we can discuss product modules. Given two G modules V and W, the tensor product V cross W is also a G module if the G action acts like a derivation would, so that we get the sum of two separate product vectors. Note that this is essentially left and right action on the product, which we can equate to the pi left and pi right representations we've discussed earlier. Hence, V times W is a G module. Now, we can totally iterate this procedure and attain a G module from any finite combination of such factors for Lie algebras. The case for associative algebras is considerably more subtle, and we'll punt that discussion to another time. And that's our show! Next time, we're going to get a little technical and discuss induced modules.